Well, hello and welcome to IRON Range Engineering. This is a little thermodynamics lesson for you. And let's see, where are we? We are in air conditioning / refrigeration, part 2. And in the last session, we identified what the different components were in an air conditioning cycle and what the temperature entropy diagram looks like. Worth drawing again quickly. So we've got let's look at it this way. We've got a hot and we've got a cold, and those are systems like a house and the outside of the house, or your car in the summer and the outside of your car. And the cold is the thing that we want to take energy out of. So we've got a couple of heat exchangers, and in this first heat exchanger, we bring in some fluid and we put energy into it. We heat it up. On the TS diagram, very quickly, we're at our low pressure. We're bringing in our fluid and we're heating it up. We are evaporating it. We call that the evaporator. Heat transfer in, evaporator. Right after that, we have a compressor. And in our compressor, we pressurize the fluid. So now it's at a higher pressure. Lower pressure, higher pressure. Now let's call this point 1. Call that point 2. And then we've got this high pressure, high temperature fluid. That's the neat part. When we pressurized it, its temperature went up. High pressure, high temperature fluid. And it's hotter than its surroundings, so we transfer heat out of it. And we know that on the TS diagram, when we transfer heat out, we move to the left. We condense it. We call that point 2. We'll call that point 3. Now we have our condensed fluid, high pressure. We need to bring it down in pressure to point 4, and we'll do that with a high friction expansion valve. Entropy goes up because there's friction. There's a quick review of what we did yesterday. So now the question transfers to analysis. An analysis means how can we find out how much heat we transfer in, how much work it takes in the compressor, how much heat can we transfer out. And the way we do that is by applying the first law of thermodynamics in steady state form and assume that the changes in potential and kinetic energy are constant or are negligible. So I'm going to write that down. Steady state, delta PE, delta KE, is very small, approximately 0. Well, let's start here with the evaporator. What goes in? H4. And then what kind of energy are we doing here? Heat in. No other heat, no other work, just heat in. And what flows out? It's that simple. Rearrange it and we'll see that Qin is equal to H1 minus H4. Where is the energy higher? It's higher at the outlet because we just put a bunch of heat into it. And how much heat? H1 minus H4. Do we know how to find H1? Yes, we do. H1 would be at our low pressure, which would be given, and it's a saturated vapor. Be HF at the low pressure. How about H4? Don't know it. We'll have to wait until we come back around to get H4. That's okay. We'll leave it there for a little bit. We'll go around the horn from 1 to 2 to 3. Actually, we're going to leave our pictures there and just go now. That was, by the way, the evaporator. Now let's do the same thing for the compressor. I want you to press pause, and I want you to write the first law for the compressor. All right. Hoping you pressed pause, and when you write the first law for the compressor, you said, well, what's going into the compressor? H1. What kind of energy are we doing in the compressor? Is it Q in, Q out, work on, work by? I hope you said, well, that's work on. That's a shaft spinning, putting energy in, plus work on. And what leaves the compressor? H2. It's a flowing system, so we use our H's. And just like that, work on equals H2 minus H1. And we know how to get H1. Do we know how to get H2? The answer is yes. We did something similar in a previous video. We do know for point 1 the entropy, and we know that the entropy at point 2 is the same. Point 2 is a superheated vapor. So if I go to the superheated vapor table at my high pressure, which would be given, I can interpolate on that table with this S until I find the temperature. But more importantly, I can find H2. All right, and that's the compressor. Moving on. Let's take a look at the condenser. That's this device up here. Steady state, negligible changes in kinetic and potential energy. What enters? H2. What are we doing? We putting heat in, taking it out, work on, work by. Well, we've got a nice arrow up there that it's heat out, so that's a minus. Minus heat out. What leaves? H3. Well, just like that, heat transfer out in the condenser. Those two words are too similar. They're too close together. Too sounding similar. So Q out equals H2 minus H3. Notice my little algebra sign switch there. And does that make sense? Where did it have more energy? At 2. So a big number minus a small number, big number minus a small number. All right, and we already found H2. Do we know how to find H3? I hear a resounding yes. I'm hearing you say, well, yes, Ron, that is HF at the high pressure. Very good. You win. H3. Boom. All right. What about that expansion valve? Let's write the first law. What goes in? H3. Is there any heat? Nope. Any work? Nope. No heat transfer, no moving parts. Nothing. Nothing. What leaves? H4. Oh yeah. Put a smile on. H3 is equal to H4. We now have H4. Yeah. Partay. Where'd it go? Right here. Remember when we needed H4? We didn't know what it was? It's the same as H3. So in an air conditioning cycle, we only need to find H1, H2, and H3 because H4 is equal to H3. Wonderful. Let's see, I'm going to check on our time here. In 11 minutes, I've got a few more minutes to tell you something cool. So, nice new piece of paper. One of the things that we haven't talked about on any of our videos yet is how to decide how effective a thermodynamic cycle is. So the question is, how do we measure effectiveness of thermal cycles? And we do it with something called an efficiency, a thermodynamic efficiency. So I'm not going to put a symbol down. I'm going to save that for another time. But the efficiency of any cycle is the desired energy transfer divided by the energy cost. Which of those three energy transfers is the one we want in an air conditioning system? It's the heat transfer in. Because the heat transfer into our coolant is the heat transfer out of the cold space. And that was the whole idea. How do we keep the refrigerator cool? How do we keep the freezer cold? How do we keep the temperature in our house nice? It's the heat we take out of the house. See that? Whoa. And put into the coolant. So the desired is our Q in, or we decided that that was H1 minus H4. What does it cost? Which of those things do we have to pay for to work on? Our refrigerator is plugged into the wall. That's the work that's being done. Our air conditioning cycle in our cars is hooked up to the electrical system. That's what we pay for, so work on. And we decided that that was H2 minus H1. So the efficiency or the effectiveness of an air conditioning cycle is the heat transfer in to the cycle over the work on. And we're going to, in one of our on-site classes, we will find an H1, an H2, an H3, an H4, and find one of these effectivenesses. All right, well, I think that's our fun for the day. My day's only going to go downhill from here. I can't do any more thermo. And anything other than thermo is it's a letdown. But I think I'll have some pudding with some whipped cream.